Hello everyone. So today I want to talk a little bit about gases, the gas phase of matter, a little bit about the physics of gases, and specifically about what's called the ideal gas law. It's a simple mathematical relationship between different properties of a gas, like the pressure and the temperature and the density and some other things. Before I get to that, what exactly is a gas? The gas phase of matter is the phase in which the particles, I hope you can see this pretty well, as I know there's a reflection on the board, but this is a diagram that's in the reading for today, and you see a bunch of balls just rattling around inside a box. This is more or less what the atoms and molecules of a gas are doing. They're just bouncing off each other, bouncing off the walls of the container that they're in, and just rattling around at high speeds. Air is mostly molecular oxygen and molecular nitrogen, and those are traveling several hundred meters per second as they rattle around, bouncing into each other trillions of times per second. Now, since the balls are in this container, like if you have air molecules inside a balloon, for example, they're bouncing against the walls of the container, and that collective bouncing against there, the impulse that's exerted on the walls of the container, that is where we get pressure. In other words, if there are no particles on the outside, then the bouncing of the particles on the inside gives a net constant impulsive force on the inside, and that's what pressure is. So when you blow up a balloon, what are you doing? You're putting more air molecules inside the balloon than there are on the outside, so that the net force against that is toward the outside, and that blows up the balloon and it gives it that sort of solid pressure, same as the air in tires. So, not surprisingly, the pressure against the side of a wall is proportional to the number density of the particles that are in there. And it's also proportional to how fast those particles are going. In other words, the higher the speed of those particles, the more impulsive force each one has against the side of the container. So, what are the implications of that? Let me just switch off the overhead. So the pressure of a gas is proportional, the symbol means proportional. It's proportional to the temperature of the gas, because temperature is a measure of how fast the gas particles are moving. The higher the temperature, the faster they're moving. I mean, that's what it means for a gas to become hotter. It means the particles are moving at a higher speed. So when you feel a warmer temperature, your nerve endings are somehow sensing the higher speed of those air molecules. And the faster they're moving, the greater the impulse that each atom or molecule is exerting against the side of the container that it's in. So not surprisingly, pressure is proportional to the temperature. I mean, it's not obvious that it's directly proportional to the temperature, but that turns out to be the case. It's also proportional to, let me move this over a little bit, to the number of gas particles that are in there. Now, N is actually the number of moles of gas particles. Remember, 1 mole is 6.022 times 10 to the 23 atoms or molecules. So, the pressure of gas particles in a container is proportional to the temperature of those gas particles, also the number of moles that are in there. Now, the size of the container makes a difference as well. The bigger the container for a given number of particles, the lower the density of the particles that are in there, the lower the pressure is going to be against the walls. So, let me just write this. The volume of the container is inversely proportional to the pressure. In other words, the bigger the volume of the container is for a certain number of moles of gas particles, the fewer of them per second are going to be rattling against a particular, and the lower the pressure will be. So everything else being the same, if this goes up, that must go down. Does that make sense? Well, you can see the mathematical proportionality here. And so this symbol means proportional. Let's make it into an equation. The constant of proportionality is called the universal gas constant. And I'll just show you what that is. So this is the ideal gas law. So here's a container. What's being related here? Well, the volume of the container is V. The number of moles of gas particles in that container is N. The temperature in degrees above absolute zero, the Kelvin temperature scale that we talked about earlier, is there. And the pressure is the impulsive force against the outside. Now, what are the units of pressure? Well, the units of force that we saw are newtons. That's the unit of the standard international unit of force. So a given amount of force against that wall, how do we quantify the pressure against the total area in there? We quantify it as newtons per area, or newtons per square meter of area. And that's called a Pascal. Let me just write that as Newton per square meter. The force per unit area of the inside area of this thing. So, units of pascals. Now the Earth has some atmospheric pressure because the gravity of the Earth is holding the gas of the Earth down to the ground. And so we're at the bottom of this sort of sea of air that's 100 miles deep or so. And the pressure at the surface of the Earth is about 101,000 pascals, 101,000 newtons per square meter. So every square meter of this board is 101,000 newtons of air pressure pushing against it. That's the pressure down here at the bottom of the Earth's atmosphere. You know that when you go swimming in a pool, the deeper you go underwater, you can feel the pressure increase on your ears, right? That's because you're under more and more of that heavy fluid, water. It's the same in the atmosphere. We're at the bottom of this deep sea of air, which is a lot less dense than water. But the pressure here is significant. And if you go up in altitude, you can feel the relief of pressure in your ears as you go to shallower and shallower depths in this sea of air that we live in. So the pressure of the atmosphere is 1 atmosphere. That's a unit of pressure. It's equal to the atmospheric pressure at sea level. It's about 101,325 pascals. That happens to be the air pressure at the surface of the Earth. On a different planet with a different mass atmosphere, it can be different. Venus, the surface pressure is about 100 atmospheres, 100 times what it is here, so that would be, what, 10 million pascals. So, okay, let me do a few problems with this. For instance, let me calculate the number of moles of gas in a cubic meter of air. Here's a meter by a meter by a meter cubed. That's a pretty large unit of volume. Let me just calculate the number of moles of gas in a cubic meter of air by using the ideal gas law. Well, the surface pressure of the Earth is 101,325 pascals. I want to find out the number of moles in a cubic meter of air, so my volume of my box that I'm calculating for is 1 cubic meter. Number of moles, that's what I want to find out. This constant, R, is about 8.31 joules per Kelvin per mole. That's the units associated with that constant. And the temperature in this room is on the Kelvin temperature scale about 295 Kelvin. So let me calculate N. So forgetting the units for a second, 325 times 1 over 8.31 times 295. Let me just see what that is. And that comes out to about, and that's about 41.3, whoops, moles of air. So inside a 1 meter by 1 meter by 1 meter cubical space of air at the Earth's surface, that's the number of moles of gas, of oxygen and nitrogen and whatever else, air is made of. That's how many moles of gas particles there are. Anyway, that's the claim that I'm making with the ideal gas law. Now notice that nowhere in here is any indication of what type of gas is involved. It doesn't even matter. So you could have a cubic meter of helium at these same conditions would still have the same number of moles in it. Now helium particles are smaller and lighter than oxygen molecules or nitrogen molecules, and at a given temperature, smaller gas particles are moving faster, and so they have a higher speed, but the pressure relationship with these other properties is still the same. It's one of the magical things about the ideal gas law, is it works for any kind of mixture of gas, regardless of what it is. So let me use this for a real world example here, and I'm going to try to estimate the number of gas particles inside this ball by finding the volume of the ball and doing this same thing with atmospheric pressure. It's going to be the same problem, except the volume isn't going to be 1 cubic meter, it's going to be the small volume of this ball. I did some measurements earlier, and I calculated the volume, and it's about 0.0027 cubic meters. So let's recalculate this. And that's about 0.112 moles. Okay, so that's the number of moles that I'm claiming is inside this ball. Now I've got this ball at atmospheric pressure. It's squishy because I've lowered the pressure of this ball to atmospheric pressure by just letting the air pressure out of it. Now I'm also going to weigh the ball, so I'm just going to weigh it on this triple beam. So it looks like it has a mass of about 322.3 grams. And I said 322.3. 322.3. Okay, so I've got the mass and the number of moles at atmospheric pressure. Now I'm going to pump more air into here. So I got a bike pump here, and I'm going to pump more moles of air into here, and I'm going to pump it to a fairly high pressure, higher than you would normally pump a little ball like this if you wanted to use it as a basketball. So I just pumped it to pretty good pressure. Now it bounces because I pumped more moles of air inside it. That means that the density of air molecules on the inside of this ball is greater than the density on the outside, which means all these air molecules are rattling against the inside of the ball, and there's more per second rattling against every square inch of the inside of the ball than against the same square inch on the outside, because I've added more gas molecules in there. So there's a net force pushing out because it's more gas particles per second are rattling against there. That is why it's solid now. It's pushing out. This ball is made of fairly strong material, so it's able to withstand expanding due to that increased force on the inside. And now I'm going to weigh it again, because I don't know if you can see, but the thing is not balanced anymore because I put more air in there, which means there's a slightly higher mass of air on the inside of the ball than on the outside, or than was in there Okay, so this is about 326.7. 326.6 grams. So let me write that over here in green. So that's after being pumped up. And now I'm going to find out how many moles of gas I put in there. So this equation, I'm going to use this equation again, except N is going to be a larger number of moles. Now what has changed in here? I've put more gas particles in. R is a constant, that stayed the same. T is pretty much constant. When I compressed the air, I heated it up a little bit, but I'm going to just pretend that didn't happen. It did change a little bit. The volume is basically the same. The ball probably stretched a tiny bit, but not very much. But the pressure is higher. The pressure is why the ball is now hard. So that's a much higher pressure. So I have to, let me just measure that pressure now. And it's about 16 psi. So, let me write this in green. PSI, that's an American unit of pressure, pounds per square inch. The SI unit of pressure is newtons per square centimeter, force per area. So we use different units in the United States from the rest of the world. So we use PSI, pounds per square inch. And I have to convert that to SI units. And the rate of conversion is a factor of about 6,900. So if I multiply this by 6,900 pascals per PSI, that's about 110,000 pascals. And I might say, okay, it was 100,000, 101,325 before, now I've increased it to 110,000. This gauge actually, it's actually higher than that. This gauge tells us the pressure above atmospheric pressure. In other words, the additional pressure inside the ball, in addition to what there was before. So I have to actually add that to atmospheric pressure. So 110,000 added to 101,325 would be 211,325, right? So everything else is the same except for that. So 211,325. Now let me recalculate the number of moles of gas in there. And that's about 0.234 moles. So according to this, I've added some moles of air in this. So what is this difference? 0.234 minus 0.112 is 221. 0.122 moles is what I've added. And that corresponds, and that's how much mass. 326.3 minus, that's 4.3 grams. So according to this, 0.112 moles of air has a mass of 4.3 grams. So I can find the molar mass of air according to what I've done. The molar mass would be, the mass per mole would be 4.3 grams over 0.1122 moles. And what is that? And that's about 38 grams per mole. Well, that didn't work so great because the molar mass of air is actually about 29 grams per mole. I'm not sure what went wrong. But anyway, I got a ballpark estimate for the molar mass of air just based on this idea with the ideal gas law. Now, I'm not sure why it was so far off. Sometimes it works better than others. But it could be that because I didn't take the raising of the temperature into account, I made estimates for this pressure gauge may not be exactly right. So, but anyway, that's a little bit about the ideal gas law. Thanks.